In mathematics, real coordinate space of n dimensions, written ℝn or ɑr̂ɛn with keyboard, is a coordinate space that allows several real variables to be treated as a single variable, with various numbers of dimensions. ℝn is used in many areas of pure and applied mathematics, as well as in physics. It is the prototypical real vector space and a frequently used representation of Euclidean n-space. Due to the latter fact, geometric metaphors are widely used for ℝn, namely a plane for R2 and three-dimensional space for R3. Definition and uses. For any natural number n, the set ℝn consists of all n tuples of real numbers. It is called n-dimensional real space. Depending on its construction from n instances of the set R, it inherits some of the latter's structure. Notably, when defined as the direct sum of vector spaces, addition and scalar multiplication are defined on ℝn. See below. ℝn is a topological space. See below. An element of ℝn is written where each is a real number. For each n there exists only one ℝn, the real n-space. Purely mathematical uses of ℝn can be roughly classified as follows, although these uses overlap. First, linear algebra studies its own properties under vector addition and linear transformations and uses it as a model of any n-dimensional real vector space. Second, it is used in mathematical analysis to represent the domain of a function of n real variables in a uniform way, as well as a space to which the graph of a real-valued function of n-1 real variables is a subset. The third use parametrizes geometric points with elements of ℝn. It is common in analytic, differential and algebraic geometries. ℝn, together with supplemental structures on it, is also extensively used in mathematical physics, dynamical systems theory, mathematical statistics and probability theory, in applied mathematics, numerical analysis, and so on, arrays, sequences, and other collections of numbers in applications can be seen as the use of ℝn to the domain of a function of several variables. Any function f of n real variables can be considered as a function on ℝn. The use of the real n-space, instead of several variables considered separately, can simplify notation and suggest reasonable definitions. Consider, for n equals 2, a function composition of the following form, where functions g1 and g2 are continuous. If x1 r, f is continuous, x2 r, f is continuous, then f is not necessarily continuous. Continuity is a stronger condition. The continuity of f in the natural R2 topology, also called multivariable continuity, which is sufficient for continuity of the composition f. Vector space. The coordinate space ℝn forms an n-dimensional vector space over the field of real numbers with the addition of the structure of linearity, and is often still denoted ℝn. The operations on ℝn as a vector space are typically defined by the zero vector as given by, and the additive inverse of the vector x is given by this. Structure is important because any n-dimensional real vector space is isomorphic to the vector space ℝn. Matrix notation. In standard matrix notation, each element of ℝn is typically written as a column vector and sometimes as a row vector. The coordinate space ℝn may then be interpreted as the space of all n times 1 column vectors, or all 1 times n row vectors with the ordinary matrix operations of addition and scalar multiplication. Linear transformations from ℝn to ρ may then be written as m times n matrices which act on the elements of ℝn via left multiplication and on elements of ρ via right multiplication. The formula for left multiplication, a special case of matrix multiplication, is any linear transformation is a continuous function. Also, a matrix define an open map from ℝn to ρ if and only if the rank of the matrix equals to m. Standard basis. The coordinate space ℝn comes with a standard basis. To see that this is a basis, note that an arbitrary vector in ℝn can be written uniquely in the form geometric properties and uses. Orientation: the fact that real numbers, unlike many other fields, constitute an ordered field yields an orientation structure on ℝn. Any full-rank linear map of ℝn to itself either preserves or reverses orientation of the space depending on the sign of the determinant of its matrix. If one permutes coordinates, the resulting orientation will depend on the parity of the permutation. Diffeomorphisms of ℝn or domains in it, by their virtue to avoid zero Jacobian, are also classified to orientation preserving and orientation reversing. It has important consequences for the theory of differential forms, whose applications include electrodynamics. Another manifestation of this structure is that the point reflection in ℝn has different properties depending on evenness of n. For even n it preserves orientation, while for odd n it is reversed. Affine space ℝn understood as an affine space is the same space, where ℝn as a vector space acts by translations. The distinction says that there is no canonical choice of where the origin should go in an affine n-space, because it can be translated anywhere. Convexity: in a real vector space, such as ℝn, one can define a convex cone, which contains all non-negative linear combinations of its vectors. Corresponding concept in an affine space is a convex set, which allows only convex combinations. In the language of universal algebra, a vector space is an algebra over the universal vector space R infinity of finite sequences of coefficients, corresponding to finite sums of vectors, while an affine space is an algebra over the universal affine hyperplane in this space. A cone is an algebra over the universal orthant, and a convex set is an algebra over the universal simplex. This geometrizes the axioms in terms of sums with restrictions on the coordinates. Another concept from convex analysis is a convex function from ℝn to real numbers, which is defined through an inequality between its value on a convex combination of points and sum of values in those points with the same coefficients. Euclidean space: the dot product defines the norm x equals square root xx on the vector space ℝn. If every vector has its Euclidean norm, then for any pair of points the distance is defined, providing a metric space structure on ℝn in addition to its affine structure. As for vector space structure, the dot product and Euclidean distance usually are assumed to exist in ℝn without special explanations. However, the real n-space and a Euclidean n-space are distinct objects, strictly speaking. Any Euclidean n-space has a coordinate system where the dot product and Euclidean distance have the form shown above, called Cartesian. But there are many Cartesian coordinate systems on a Euclidean space. Conversely, the above formula for the Euclidean metric defines the standard Euclidean structure on ℝn, but it is not the only possible one. Actually, any positive definite quadratic form Q defines its own distance, square root Q. But it is not very different from the Euclidean one in the sense that such a change of the metric preserves some of its properties. For example, the property of being a complete metric space. This also implies that any full-rank linear transformation of ℝn, or its affine transformation, does not magnify distances more than by some fixed C2, and does not make distances smaller than 1C1 times a fixed finite number times smaller. The aforementioned equivalence of metric functions remains valid if square root Q is replaced with m, where m is any convex positive homogeneous function of degree 1, i.e., a vector norm. Because of this fact that any natural metric on ℝn is not especially different from the Euclidean metric, ℝn is not always distinguished from a Euclidean n-space even in professional mathematical works. In algebraic and differential geometry, although the definition of a manifold does not require that its model space should be ℝn, this choice is the most common, and almost exclusive one in differential geometry. On the other hand, Whitney embedding theorems state that any real differentiable m-dimensional manifold can be embedded into R2 meters. Other appearances. Other structures considered on Rn include the one of a pseudo-Euclidean space, symplectic structure, and contact structure. All these structures, although can be defined in a coordinate-free manner, admit standard forms in coordinates. Rn is also a real vector subspace of Cn which is invariant to complex conjugation. See also complexification. Polytopes. In Rn there are three families of polytopes which have simple representations in Rn spaces, for any n, and can be used to visualize any affine coordinate system in a real n space. Vertices of a hypercube have coordinates where each xk takes on one of only two values, typically 0 or 1. However, any two numbers can be chosen instead of 0 and 1, for example -1 and 1. An n hypercube can be thought of as the Cartesian product of n identical intervals on the real line. As an n-dimensional subset it can be described with a system of two n inequalities. Each vertex of the cross polytope has, for some k, the xk coordinate equal to plus or minus 1 and all other coordinates equal to 0. This is a dual polytope of hypercube. As an n-dimensional subset it can be described with a single inequality which uses the absolute value operation. But this can be expressed with a system of two n linear inequalities as well. The third polytope with simply enumerable coordinates is the standard simplex, whose vertices are n standard basis vectors and the origin. As an n-dimensional subset it is described with a system of n plus 1 linear inequalities. Replacement of all with less than gives interiors of these polytopes. Topological properties. The topological structure of Rn can be obtained not only from Cartesian product, it is also identical to the natural topology induced by Euclidean metric discussed above. A set is open in the Euclidean topology if and only if it contains an open ball around each of its points. Also, Rn is a linear topological space, and there is only one possible topology compatible with its linear structure. As there are many open linear maps from Rn to itself which are not isometries, there can be many Euclidean structures on Rn which correspond to the same topology. Actually, it does not depend much even on the linear structure. There are many non-linear diffeomorphisms of Rn onto itself, or its parts such as a Euclidean open ball or the interior of a hypercube. Rn has the topological dimension n. An important result on the topology of Rn, that is far from superficial, is Brouwer's invariance of domain. Any subset of Rn that is homeomorphic to another open subset of Rn is itself open. An immediate consequence of this is that room is not homeomorphic to Rn if Mn, an intuitively obvious result which is nonetheless difficult to prove. Despite the difference in topological dimension, and contrary to a naive perception, it is possible to map a lesser dimensional real space continuously and surjectively onto Rn. A continuous space-filling curve is possible. Examples. N1 cases of 0 N1 do not offer anything new. R1 is the real line, whereas R0 is a singleton, understood as a zero vector space. However, it is useful to include these as trivial cases of theories which are appropriate for different n. N equals 2, n equals 3, n equals 4. R4 can be imagined using the fact that 16 points, where each xk is either 0 or 1, are vertices of a tesseract, the 4 hypercube. The first major use of R4 is a space-time model. 3 spatial coordinates plus 1 temporal. This is usually associated with theory of relativity, although 4 dimensions were continuously used for such models since Galileo. The choice of theory leads to different structure, though. In Galilean relativity the t-coordinate is privileged, but in Einsteinian relativity it is not. Special relativity is set in Minkowski space. General relativity uses curved spaces, which may be thought of as R4 with a curved metric for most practical purposes, though any of these structures does not provide a metric on R4. Euclidean R4 also attracts the attention of mathematicians, for example due to its relation to quaternions, a four-dimensional real algebra themselves. See rotations in four-dimensional Euclidean space for some information. In differential geometry, n equals 4 is the only case where ℝn admits a non-standard differential structure. See exotic R4. Generalizations.